Well, it's a big hello and welcome to everybody to part 2 of our Heathkit IT-12 signal tracer repair. Well, I'm hoping that you were with me for part 1 of the video where we did an initial inspection on the signal tracer. There's definitely some kind of ferocious looking beastie in here. Luckily I think it is fairly desiccated. I've got no idea what it is. What sort of bug is that?
If you've seen one of these, then you've seen a kissing bug. While they're not all that common, their bite can be deadly.
Often called kissing bugs are insects that suck blood and bite the faces of people while they're asleep. Some of these kissing bugs carry a parasite known as Trypanosoma cruzi. This is a parasite that could potentially cause Chagas.
We also replaced some of the resistors that have gone high in value. So I think we're about at the point now where we can actually put some power on it. But before I actually power it off the mains, I think I want to try to have a go at reforming the capacitors. So you can see we've got this tall aluminium can here, and this is our 3-stage capacitors. It's actually got 3 capacitors inside this can. So there's actually 2 capacitors which are rated at 50 microfarads each, and they're actually the main smoothing capacitors. And then we've got another capacitor in here which I think is about 20 microfarad, and that's used as a bypass capacitor in the pentode output stage. Now when it comes to capacitors, it's actually quite a controversial subject. Everybody has their own way of dealing with them. Now the problem with electrolytic capacitors is over time they stop being capacitors and can start becoming resistors, and that's a problem because they start dissipating power and they get very hot and start smoking, and worse than that, they have a habit of also shorting out the transformer, which can do irreparable damage. They have got like a wet electrolyte chemical inside. Over a period of years that chemical dries out and the capacitor stops working effectively. Now there's 2 techniques that you can really employ. One of them is to actually reform the capacitor. Now what reforming is we just pass a low voltage in to start with that's current limited, and we actually gradually turn up the power supply and we allow the insulating material to reform on the capacitor plates. Now that sometimes works, it sometimes doesn't. I've never had a particularly good success doing that. The other thing that you can do, and the technique that I always employ, is I just replace them on site. If I see an old electrolytic capacitor, I just replace them, because in my experience if you don't replace it, it will still fail at some point in the future. These people say they reform them, and yeah, and you maybe will get away with reforming it. I've not found it to be a reliable repair, and the worst case is, you know, you go downstairs to make a cup of tea and then you come back upstairs to where my workshop is, and you find that your workshop's full of smoke and there's lots of tar leaking out the bottom of your main power supply transformer, because when you weren't looking, this capacitor that looked fine decided to go short circuit. Yeah, I've not had a good experience with it, but this piece of equipment is a little bit more modern than, you know, some of the radios I play with of the 1930s and 1940s. I'm not exactly sure how old this is. I'm guessing maybe 60s or 70s. I'm not totally sure. I'm going to go for 60s maybe. So this being a little bit more modern, maybe we'll have better luck with the reforming the capacitor. I don't know. I'm willing to give it a go in the name of science, so let's give that a try. So I've just crudely scribbled down a little mock-up of our capacitor here. So here's a can of our capacitor, and inside the capacitor we've got these 3 separate capacitors, 250 microfarads and 120 microfarad. So what I think I'd like to do is, before we try reforming these, let's just measure the capacitance value and make a note of the ESR, because that might give us some indication of whether the capacitors are good or bad, and also to see if the reforming process makes any difference. Now it's quite possible that this piece of equipment has been in use in America before it was shipped to me. I mean, the worst case is it's just been stuck on a shelf for 30 years and the as I say, the capacitors will have lost their internal insulation. So sometimes, you know, it's better to periodically run your vintage equipment just to keep the capacitors reformed. So I don't know the history of this, so let's just go ahead and we'll try and measure each of these capacitors and see what it says. I don't know if I'll be able to get a good measurement off this, because obviously we've got components in circuit. Okay, we've got something that's come up as 53 microfarad at 0.3 ohms ESR, so we'll write that down. I don't know off the top of my head whether the SR value is good or not, because it's related to the voltage of the capacitor, so I'm going to have to just look that up on a little voltage chart in a minute. Let's see if I can find the other unit, which I think will be there. So the second of our 50 microfarad capacitors in this can, it's actually coming up as 50.06, so I'll just write that down. And the ESR is slightly higher at 0.4 ohms. And we just finally got to get on the 20 microfarad now. Don't know if I can get access to that very easily. I think I can maybe get on it on the other side here. I think that might be it. That's where it joins onto the valve. Well, that's coming up as in-circuit leaking. Now I think it might not be giving us a capacitance reading because it's actually being shunted by a 300 ohm resistor, so I think maybe my peak atlas here is detecting that 300 ohms and saying it's a leaky capacitor. The reason I think that it might be okay, and I could be wrong, is because this has actually only got a relatively small voltage across it in operation in this cathode bypass position. It's not got a lot of voltage across it, so yeah, I'm kind of thinking that usually those are okay, but I'm not sure. So what we are going to do is we're going to have a go at reforming it, and we'll, the honest answer is we'll just have to keep our eye on it. Just make a note that that cathode bypass capacitor, it's only 25 volt working, so I have to be careful not to exceed that when we try to reform it. Whereas I think the others are, I think they're 150 volts, aren't they? Yeah, 150 volt. Now, in a valve radio that often has a tube rectifier, the way that most people do it is they actually plug the radio into a variac, maybe via what they call a lamp limiter, and they turn up the voltage very slowly, and that's how they reform the voltage across the capacitor, how they bring the voltage up. That's not a good way of doing it, and the reason it's not a good way of doing it is because you don't really get any output from the rectifier until you've got the mains voltage turned right up, and the reason you don't get an output is because the filaments won't be hot on it. So if you want to reform a capacitor in a tube radio, what you should probably do is you should take out the valve rectifier and link it out with a solid state silicon diode, and then you can turn the power up more gradually using the variac and allow the capacitors to reform. That's a better way of doing it. I'm not going to do it that way either. What I'm going to do is I'm going to use a DC power supply, because I just happen to have a high voltage power supply, and I can actually turn it up to about 90 volts with that, which is should be more than good enough to start reforming these capacitors. So this is my very dusty and dirty old Farnell power supply, and it's useful because it goes up to 90 volts on the output. So what I'm going to do is on the positive output here, I'm just going to put a 10k resistor. Again, there's no particular reason why I'm using this value. It was what was on the bench in front of me, and you know how lazy I am. If it involves getting up and searching for components, I just use what's on the bench. And this is just there to provide a little bit of current limiting. Now this power supply does have current limiting on it, but it is just better to actually just power it up via this current limiting resistor here. So we're going to be able to see the voltage output from the power supply here, but what I also want to see is a voltage across the capacitor. So we need to take the voltage measurement across the other side of our current limiting resistor. So we'll just get our fluke meter out, put that there. And we'll have to be a bit careful putting our fingers in there, because as we start to turn this voltage up we could of course get a belt off it. So let's turn our power supply on now. So we can see the current that we're drawing. Well, the meter's at 0.007, so that's just floating a little bit. And we've got 0 volts on here. So if we start to turn the voltage up now on our power supply, what should happen is these capacitors should start to charge, and the voltage in our fluke meter should come up. If we've got a badly short circuit, or these capacitors aren't reforming correctly, what we'll find is that we'll find a big difference between the voltage indicated. We'll get a low voltage indicated on this meter, but a high voltage indicated on this one. And if we get that, that means that the capacitors are conducting, they're not acting like capacitors. Anyway, let's turn up the voltage and see what happens. Alright, well I can see almost immediately these two meters are following each other reasonably closely, so just immediately that makes me think that probably there's not a lot wrong with these capacitors. The way I look at these things is we're not in a race, so take it nice and steady. I'll probably let this reform for about an hour. I'll gradually keep turning the voltage up and see how we go. So I've had these capacitors reforming for about 30 minutes now and we're up to 50 volts. Now you can actually see that there is a bit of a discrepancy here between our 47 volts on our fluke meter, which is the voltage across our capacitors, and the 54 volts that we're outputting from the power supply, and that would lead you to believe that we're actually dropping a few volts here across our current limiting resistor, but actually it looks like it's just actually a slight problem with the calibration on this meter, because you see 47 volts. If we actually go to the output of the power supply, it shows 47 volts as well, so it's just a flaky meter. Maybe we'll have to see if we can calibrate this at some point. Always a good idea just to check that the capacitors aren't getting hot. Certainly wouldn't expect to, because we're not drawing any current really, so it appears that this capacitor is in good condition, it's reforming nicely. So I just need to test both sections of our 50 microfarad smoothing capacitor, so let's just check one side. There's 102 volts on that, and there's 102 volts on the other. So I'm very happy with that. That's a good capacitor, no problem. So we have got one electrolytic capacitor left to do, and that's this 20 microfarad, which is used for the cathode bypass. I don't need to tell you about the risk of leaving capacitors charged up. I mean, one, you can get a nasty electric shock off them, but two, the worst thing than getting an electric shock, of course, is we might plug our ESR meter into it and damage the meter. So always a good idea to discharge capacitors. So I'm going to clip one side to the chassis again, and it's a little bit difficult. We can't get a direct connection to the capacitor. All I can actually do is get a connection to the wire that feeds it, which is that wire there. So can I just get into there? I think we've got that on. So let's just make sure that capacitor has got some voltage on it, and of course I don't need to worry about poking around so much now. Can I get to the leg? I think it's that one. No, it's not. Yes, it is. So I think what I'll do is I'm just going to go ahead and I'm going to just disconnect the cathode bypass resistor here. We've got a 300 ohm resistor. I'm just going to disconnect that, because that will just isolate the capacitor here, the 20 microfarad section, just to make sure that there is you know, nothing else interfering with the readings that I'm taking. But it does actually look like we've got a bad capacitor section, and I was hoping to avoid that, because well, it's quite nice, isn't it, this capacitor with its 3 sections. It's not the sort of thing you can just go down to the shops and easily replace, is it? Interestingly, I've just spent about an hour dismantling this circuit and trying to get back to the problem of not being able to charge this capacitor, because I was fairly convinced it had gone short circuit, although when I put the ohm meter on it, of course, it looked fine. I eventually traced the problem to actually the connecting lead that I was using, in that it seems to go intermittently open circuit and short circuit. Hopefully you can see that on the ohm meter. But yeah, God, these things are just sent to try us, aren't they? All part of the game. But you can see here that they've stripped the end of the wire where it goes into the crocodile clip, but it's barely making contact. I can actually see all the exposed strands, and there's just 1 or 2 wires which are actually crimped together, so it isn't like they've even bothered to solder these together or even make a good job of crimping them. So of course that's why we're having so many problems with these. I think I'll probably end up throwing all of these leads away, because I've had nothing but trouble with them. Now, of course, not unsurprisingly, now I've bothered to correct the problem with our jumper cable, we've actually got 24 volts back on this capacitor. So, oh well, these things are sent to annoy us, aren't they? Of course, everything works better when it's laminated. So as you can see, I've just gone ahead and I've printed myself off a crib sheet for our ESR values, because they do vary quite a lot with the voltage rating for the capacitor. So we had a 50 microfarad, well the nearest we've got on the chart is 47, so that'll do, and it was 150 volt, but the nearest we've got is 160. So we'll just go along there, and it says that the maximum ESR value is 1.6 ohms. So the original value that I recorded using the ESR meter was 0.38 ohms, so we're well under our 1.6 ohm maximum there. But I do wonder if it's changed at all now that we've tried some reforming. So we'll just measure it again and see if it's made any difference. It hasn't changed, it's still 0.38, so reforming made no difference. Let's go to the second smoothing capacitor. Oh, that's come up as 0.38, so that could be a little bit better. 0.38. Let's see if we can get on the one that's we couldn't get at before, which was the cathode that's given us all the problems. And okay, that's still coming up leaky with an ESR of 1.42. And as I said, it's coming up leaky because it's being shunted with a 300 ohm resistor. But I do think that capacitor's probably okay. And of course the ESR value, the maximum for that was 6.2 ohms and we're getting 1.42, so the ESR looks good anyway. Well, I think after all our capacitor reforming shenanigans, I'm just going to plug this thing in now because I'm annoyed. So I'm just going to plug it in and we're just going to try it. Normally I might run this up with a lamp limiter, I'm not going to do that, but I am running it from the isolation transformer because, as I said, the body of this isn't earth. And I've also got our watt meter plugged in here so we can actually see how much power it takes. I think these are meant to take about 20 watts. I'll try switching it on. Well, it's drawing 25 watts at the moment, so that seems about right. So we've got some hum now, and it does seem to change as I move my hands around. Okay, that seems okay. First thing I'm going to do before I get too excited though, I am just going to check that there's no leakage onto the grid of our output pentode valve. So I'm just using our voltmeter to monitor the input of the grid on the pentode valve. And I don't know if you can see the needle is, well, the reading is steadily increasing. So I think that the coupling capacitor may be leaking slightly. It may not be because it's still only 0.06 of a volt. But it is steadily, you know, you can see it's climbing, so I think as a precautionary measure we are just going to swap that out. At the end of the day, this capacitor might absolutely be fine, and you know, I might just be kind of replacing it for the sake of it. But in my experience, the problem that you will have is that if these things do start to leak current, you'll get an excessive plate current in your pentode output valve, and you know, basically it'll damage the valve, it'll burn the valve out, and a valve is obviously much more expensive to replace than a 50 pence capacitor. So, you know, if in doubt, change them out. And I'm also going to be changing this capacitor out for one that's rated at 1000 volts. So we've gone up a little bit as well. Well, I think while I'm working on this section of the circuit, I may as well try to see if I can replace this 0.05 microfarad capacitor with something with a higher voltage rating, because the one that's in here at the moment is just a little ceramic, and yeah, I don't know what I'm going to be probing in here, but I wouldn't want that ceramic to break down, and it's an old one, so I'm going to see if I've got something with a nice 1000 volt rating to put in place of that. Well, you know what, it's Bring an Idiot Day to the All Gear No Idea workshop today, because I've just gone ahead and I've put 0.047 in as opposed to 0.0047. Ah, God, what an idiot. Don't know what's going on today. You know, this is one of them days where I should have just stayed in bed because everything I do is going wrong. You know what I really need to do? I need to spend a little bit of time going through my capacitor collection, because I've got drawers and drawers full of capacitors, and what I have a habit of doing is I buy capacitors and then they're on my desk and I get annoyed because they're untidy, so I just go ahead and I stuff them in a drawer, and I usually stuff them in the wrong drawer, which is what I've done here. I've got them out the right box, but we've got the wrong capacitor value in. Now, as it happens, the capacitors that I'm replacing it with, they've got a higher voltage rating anyway. These are 1000 rather than 400, so they will be better. Fortunately, these 1000 volt rating ones are actually a little bit bigger, so I think they're going to slightly get in the way of our Magic Eye tube. I think we'll get it in. So I'm just having a go at the capacitor now that's on the wiper and feeds the grid of the first triode preamplifier. So that other capacitor was really tight to get in, perhaps probably a bit too tight to be honest. I've got it stuck up in the air a little bit, and I've had to put some heat shrink on one side of it so I don't run the risk of it coming in contact with the bottom of the support. There's a little bracket that holds this magic eye valve in, and if I'm not careful it's going to hit that. Now I'm afraid this isn't actually the neatest job in the world, and I've got to admit I really did struggle to get these two new capacitors in. They're both the same microfarad rating, 0.0047, but this one is the main input capacitor. This is now rated at 1000 volts, and then the first grid coupling capacitor, the first stage of our triode preamplifier, that's now got a 400 volt rated cap in. So this should, you know, in theory be a little bit safer. And of course what actually kicked this off is we've got the coupling capacitor between the output of our preamplifier now going into the grid of our pentode there, and that's fallen now to about 0. So we did have a bit of leakage on that capacitor, and also the volume appears to have come really up quite a lot. And let's go ahead and also check the voltage on this probe when we put it into the noise setting, because I want to make sure I've got it turned off is the first thing I want to do. So what's that? Turn the noise function on. Oh, it doesn't seem to put anything on it. I wonder why that is. Well, it looks like again it was another case of idiot operator error, because unfortunately the probe, I didn't have it turned on to the audio setting. I had it on the RF setting, so the noise tracer doesn't work. So if we actually switch it on now, you can see we're getting 122 volts on the tip of the probe. Turn it off again. So we're going to have to be a bit careful with that, aren't we? Well, that seems to be doing something. It's making some noise, so I'm guessing it's working. Still got to add our earth connection back on the back of the probe here. We're going to have to sort that out before we can use it. So I've just had a delivery from Amazon, and they've delivered me a cable which is, in theory, an American cable. So this should fit our American power supply, which it does. And this is a 3-core cable with the third core being an earth. So I was actually complaining about whether or not we should earth this, so I've bitten the bullet. We've bought an earth cable, so I'm going to go ahead and I'm going to install this earth cable now. So goodbye old mains cable. And I guess I will keep hold of this because I don't know, maybe I'll buy some other gizmo from America. Or keep it maybe just to make some form of test lead out of. I'm not sure. Let's keep hold of it anyway. It might come in. Got a whole garage and shed full of equipment that might just come in for something one day. So replacing the mains cable in our signal tracer, it's given us the opportunity to demonstrate this new tool that I bought months ago but haven't had a chance to try it. So what this is for is it's for actually pressing down on these strain relief glands. It squeezes them together, which in theory makes them easier to put on and take off, because well, if you've ever tried to do it, they can be very difficult to get off. So I'm kind of hoping this new wonder tool is going to make a difference. So I assume we grab it like that and squeeze it. I assume we do. Well, that didn't do anything. You would think you would squeeze it like that. Or do you do it like that? I can't think you would do it like that, would you? No, it must be like that, surely. Well, so much for the wonder tool. That's rubbish, isn't it? I think the problem may be it's already squeezed down kind of fully. Let's go back to some normal pliers, see if that does any better. Some days you just can't get a break, can you? This is definitely one of them days. Of course the instructions it comes with tells you everything, apart from it doesn't actually show you how to do it. So I've gone ahead and I had to remove the original cable clamp because it won't fit the new wire, because this new wire is a lot thicker with having 3 cores, and also with it being a more modern wire they have more insulation on them, so it's a thicker wire. So what I have done is I found one of these strain relief grommets to use. It's not a perfect fit, but I think it's going to be good enough. And I'm not going to do it now, but on another day I'm going to improvise some kind of cord grip that will go on the inside of here, because at the moment it would be possible to pull this out because it's not really tight enough. So what I will do is I'll get a piece of plastic and make like a little clamp assembly to squeeze this together, so you won't be able to pull the cord out. But I think that is going to be a job for another day. So what I need to do is I need to reconnect these up now. Seems strange to me when I look, we've got these black and white wires. Of course, this being an American cable, it's in their standard colours. Obviously we'd be on brown and blue in the UK, so it's a bit surprising when you just encounter these different coloured cables. So I'm cutting the actual live and neutral wires relatively short, and we leave the earth wire long. And the reason we leave the earth wire long is that if you do rip the cable out, the earth wire wants to be the last thing that gets ripped out. So in theory, the live and neutral will get pulled off the piece of equipment before the earth will get pulled off. So that's why we do it like that. So I'm going to go ahead and I'm going to fit this earth wire to the chassis of our signal tracer, and I've also just gone ahead and I've drilled another hole in the back cover because I'm going to earth the back cover as well. Now the other thing that I've been wrestling with is there's actually no fuse in this, and I find it a little bit interesting because you guys in America don't have fuses in your plugs either, do you? So I'm a little bit kind of confused of how you guys don't have more house fires than you do, because if you don't fuse the equipment and you don't fuse the plugs, are you relying on the fuse in your I don't know, your consumer unit, your fuse box? I would have thought that that fuse box has got quite a big fuse in it, whereas something like this only wants to have a 1 amp fuse in it or something like that. But I did intend to fuse it, but just looking around inside it, it's actually quite difficult to fit stuff to. I mean, I'd probably want to drill another hole in the chassis here somewhere, but more or less wherever you drill, you end up coming up on top of a tag strip or, you know, going through the bottom of the transformer. And, you know, the back cover goes on here, so you can't put bolts or studs sticking out. So I'm not exactly sure how to add a fuse to this. I think I will have a think about it and try and add one though. Now I'm sure I said earlier that you shouldn't use this fixing for a tag strip as an earth. You should have a dedicated earth, and I'm breaking that rule after berating others. But again, for the same reason that it's difficult to fit a fuse, there's not many places on here I could actually drill a separate bolt to put the earth wire, so I'm going to utilise an existing fixing. At the end of the day, I'm just doing this for myself. I'm not a manufacturer and I'm not selling it to anybody. But the way I'm doing it here, well, it's not to code. Now I've got to admit, I've actually found this thing really quite difficult to work on. You know, valve gear, there's always loads of room inside it, but even now, you know, I'm trying to get this tag strip on, and I'm just fighting with everything. You can't quite get your hand into anything. You know, you try to put your hand in there and it's hitting the transformer on top. You know, you try and get your hand under the chassis and you're hitting the magic eye valve. It really is, in many ways, it's kind of a miniature piece of equipment, this. There's a lot less room inside it than there is a valve radio or something like that. Yeah, I don't know what it is, but this thing has just been determined to fight me every step of the way. Sometimes you get jobs like that, don't you? You know, sometimes the simple, quick jobs, because I made the video the other day of me taking this apart, and I literally thought that it'd just be 10 minutes to put the power onto this thing and we'd be kind of finished. It was going to be a very quick video, this. Yeah, sometimes you just get it wrong, don't you? And I've certainly got it a little bit wrong here. I'm going to leave that a bit loose for now because I might have to twist it round to get access to everything. Now before, it wasn't using a polarised connector, so you didn't actually know which of the mains leads, which of the live or the neutral. You didn't know which one was connected to the switch, because of course you could just plug the non-polarised connector in either way around. Well, now we've actually got a 3-pin plug, it's polarised, so I want to actually send the live, I want to send the yeah, the live connection. I want to send that to the switch because of course you want to, whenever you're working on a piece of equipment, you want to switch the live off. I just use this air duster to cool down the joint because what happens if you've sold a PVC cable, even the terminal gets so hot, even when you finish soldering, what will happen is it's got enough residual heat to start melting the flex. So that's why I just give it a bit of a blow. Okay, that's pretty tight. So in theory now, if we've done everything right, the braiding, the outer body of our probe here should actually trace all the way through to our earth pin on our plug. Which it does with 0 ohms, so that looks okay. Well, I guess it's time to plug in and have another go. Well, I've gone ahead and I've plugged everything back in and it seems to work. You get a fair amount of hum when we touch the tip. The magic eye valve here, I don't know if I've got it lined up. I'm not sure if the opening should point to the top or not, but as I've said with most magic eyes, it seems to be just fairly useless and pretty much does nothing of any use whatsoever. I mean, I know what the magic eye should do. It should open and close, and it is doing that, but yeah, why? Just why? Anyway, if you like magic eyes, leave it in the comments. So I think what we need to do is we just need to check out this probe and try to put an earth strap back on it, because we are missing that at the moment. And I also think that we maybe have a few things that are a bit loose, so we need to address that. So let's just turn everything off and let's open up this probe and have a look inside. Does seem to pick up quite a lot of mains hum, this thing, and I think maybe the screening coax which is used perhaps isn't the best. There is also just quite a lot of electrical interference in this room, so that might not be helping. I'm guessing all this should splurge out the front end. So you can see there's nothing really very exciting inside here. It really only consists of a germanium diode and a capacitor, and then we've got a switch which actually brings the diode and the capacitor into circuit. So when you're using this in the audio mode, the diode and the capacitor is switched out. But when you want to use it to probe an RF circuit, it actually allows the incoming signal from the tip here, it allows it to come in, and that gets just demodulated because it's just a diode detector. And then I'm guessing that the capacitor maybe just does a little bit of smoothing to remove the RF part of the wave. Now when I was playing with this earlier, it was certainly sounded very, very kind of scratchy, and I think the reason it sounded so scratchy is because I think this braid is making a very intermittent connection on the body of the probe here. So depending how you hold it, sometimes it makes a connection and sometimes it doesn't. And I think this tip here is maybe designed to unscrew or something like that, but it doesn't want to unscrew. It actually unscrews it from the end. I think I might take these ends off and give them a bit of a clean. Ah, right, okay, so it looks as though the only function of this, I thought maybe the end of this you could take it off to take the probe tip out, maybe change it for a sharp one or something like that, but I don't think it works like that. All this actually is the wire that comes from the diode here on the back. It just goes through the centre of the probe here, and I think it comes out and then this is just a retaining ring to actually clamp it together. So these aren't designed to unscrew. That's my mistake. And of course in normal operation I think this should all be screwed together and should be tight. So we'll screw that back up because it doesn't want to be undone. I suppose while we've got the probe open we should just check that germanium diode is okay, because it certainly wouldn't be unusual for them to get blown and go open circuit. Okay, 0.3 of a volt, 0.35, so that's about what we'd expect, isn't it? So that's okay. Well, I think we need quite a thick piece of braid sticking out here, so I was just going to replace this with a wire, but I think if I put a wire in it wouldn't make a good contact, and also wires are quite inductive, and that would probably be a problem at the RF frequencies, so a braid is better. I'm not sure I've got anything that will be suitable though, so I might just have to go and raid the junk box and you know, see what we can find. I do think it'd be worth cleaning up the inside of this aluminium though, to make sure we have as good a connection on the braid as it's possible to have. So I think we'll do that first. And I'm guessing while we've got this apart, it probably hasn't had any switch cleaner in it in the last 30 years, so let's do that. Now my granddad was quite into electronics, and I can remember as a kind of a young child finding all his radio magazines and stuff, and you know, back in the day this kind of stuff would have been advertised in the you know, the radio amateur magazines and stuff like that, and I remember seeing pictures of this probe in, you know, various publications, and I don't know, for some reason I thought it was just tremendously futuristic, even, you know, even back 30-40 years ago. I just thought that, you know, the probe, I was going to say it looks quite phallic, and I guess it does, but you know, it just brought up the idea of rocket ships and stuff like that. Right, so what I'm going to do is I'm just going to get something to clean the inside of this tube so we can make the best possible electrical connection we can against this braid. I'm kind of surprised that they didn't actually bother to try to make a connection to the body of this switch here, because if they'd have done that, you would have actually been able to earth it through the fixing screws on the front. I'm wondering if I'd be able to just solder a little link wire on, because I do think it would probably improve the earthing of this probe. Okay, that should be a bit cleaner. Right, okay, I'm going to go away and I'm going to see if I can find a piece of braid or something to replace this. Sometimes what you can do is you can get an old piece of coaxial cable and you can actually strip the outer core off, and that leaves you with a nice piece of thick braid. But let's see what we've got in the junk box. So this is what I'm going to use to replace our missing ground strap there. I think it should be okay. And I am also going to just give it a bit of insulation. It probably doesn't need it, but I'm going to do it anyway because I can. Now this is the piece of tubing that I've got to insulate it with, and unfortunately it's quite a tight fit, and I've tried to push it through, but when you try to push it through it just swells up and it won't go. So what I'm going to do is I'm going to solder a thinner wire onto the end of here, and I'm hoping I'll be able to pull it through then. Now, speaking from experience, I know that this piece of braid is going to get very hot very quickly, because you know, copper's a great heat conductor. So let's just solder a wire onto it. Now at the other end I'm going to put this crocodile clip that I found. Yep, that's definitely got it now. Yep, that's gone on there. A terrible feeling then that wouldn't be able to fit the crocodile clip through the tube. That'd just be the sort of thing I'd do, wouldn't it? So hopefully that's going to work. I think the next thing to do is actually give this thing a test.